Good evening, my name is Valeriano Villar and I'm going to answer the quiz for number 2. So this is my solution. Okay, so let's solve for the problem number 1. So the problem is an ideal auto engine operating on the hot air standard with K is equal to 1.34 has compression ratio of 5. At the beginning of compression, the volume is 6 cubic feet and the pressure is 13.75 psi and temperature is 100 Fahrenheit. During the constant volume heating, a 340 BTU are added per cycle. Let's find for percent clearance, temperature and pressure just before expansion, and efficiency, mean effective pressure. So let's solve first for the percentage clearance. So before that, writing the given is being very important. So the given are given. We have the compression ratio, which is 5. We also have the key. We have 1.34, and we have the volume for the initial volume is 6 cubic feet, and the initial pressure we have 13.75 psia, and temperature 1 is equals to 100 Fahrenheit. So let's solve for the percent clearance. So percent clearance. So we have the equation C is equals to RK is equals to 1 plus clearance over clearance. So by manipulating the equation, we can get C is equals to 1 over the compression ratio minus 1. So let's substitute the value. C is equals to 1 over the RK, 5 minus 1 is equals to 1 over 4, or this is 0.25, or this is 25%. So this is the percent clearance. Let's go for the pressure and temperature just before expansion. So I'm getting the temperature before expansion, the T3 we have the equation, the heat added is equals to mass times the CV times T3 minus T2, but we don't have the mass, the CV and T2, so let's get them one by one. So let's go first for the mass. So let's go first for the mass, M. So from the equation, PV MR is equals to MRT. By manipulating the equation, the M is equals to PV over MR IRT. So by substituting the values, we have the pressure of 13.75, that is PIA, and the volume is 6 feet. But we're now going to we're now going to make it inches. So let's multiply 100. So let's multiply 144, that is inches per feet, over, we have the R of the constant R, which is constant R of air, which is 53.34 times the temperature. So in using this formula, always make it the value absolute. So let's add a 459.67. so our M is equal so our M is now equal to 0.3977 pound mass. So we have now our mass. Now let's solve for CV. So CV is equals to, we have the equation CV is equals to R over K minus 1. So we have the R 53.34 over the K 1.34 minus 1. So we have the value of CV of 156.88. So let's solve for the temperature 2. So for temperature 2, from the process 1 to 2, which is isentropic, T2 is equals to T1 times RK raised to K minus 1. Let's substitute the value. We have 100 plus 459.67 raised to the K, which is 1.34 minus 1. So RT2 is equals to 967. So using this equation, we can get T3. So by manipulating equation, T3 is equals to QA over mass CV plus T2. Substituting the value, we have the QA from the given. So let's write it here, 340 BTU. So 340 BTU, but cannot use it in this unit. So let's have the constant 778 feet per mass, foot pound over BTU over the M. The M we have here 0.3977 lbm, and we have CV of 156.88 plus our T2 967. We have the temperature before expansion as 5,210 Kelvin. So now let's go for the pressure, which is P3. Getting this P3, we need P2, and we can get P2 from the 1 to 2 process. So we have P2 B2 is equals to K, and P1 V1 raised to K. So we have P2 is equals to the P1 13.75 times the V2 V1 over V2, which is the V1 over V2, which is the RK. So let's write it here, the RK 5 raised to K. We have 54. So our P2 is equal to 118.8290. So we can get P3 from the isometric process. P3 over P2 is equals to T3 over T2. So our P3 is now equals to the P2 118.90 multiplied to T3 5,210 over the T2, which is 968. Our pressure at before expansion is 639.6. that is PSIA, or pound per square inch at absolute. So we have now the number this to. So let's solve for efficiency. So efficiency is equals, we have the equation for efficiency, 1 minus 1 over RK raised to K minus 1. So we have already this value, so we have 1 minus 1 5 raised to 1.34 minus 1, and our thermal efficiency is equals to 0.4214, or this is 42.14%. So let's solve for the pressure, mean pressure. So the equation for this is, we have work net over the volume displacement. So work net, the volume displacement is equals to V1 minus V2. Okay, so let's get the work net. So work net is equals to, from the equation, thermal efficiency is equals to work net over the heat added. We have this value, so we can get the work net. Work net is equals to 0.4214. So this is the thermal energy, thermal efficiency. So and 344 the heat. So we can get 143.28 BTU, since this is BTU. Okay, so we don't have V2, so let's solve for V2. V2 is equals, we have the equation, the compression ratio is equals to V1 over V2. So let's solve V2 by manipulating the equation. Let's V1 is equals to 6 feet over the RK 5. So we have 1.2 feet. So let's solve for the wind pressure. So we have the work net. We already have the work net 143.28 it's the point 143.128 BTU, and we can cancel the unit if we don't convert the unit. So let's convert first. We have 778 foot-pound per BTU. So let's cancel the BTU, and for V2 we have 6. We have 6 minus 1.2. So this is cubic feet. So okay, so solving, we can get the bin pressure is equals to 161.3 psia. Okay, so we have the problem for number 2. An ideal diesel cycle with overall value of K is equals to 1.33, RK is equals to 15, RC is equals to 2.1, pressure 1 is equals to 97.9 kPa. So let's find the pressure just after compression and mean effective pressure. So let's find the P2, which is the pressure after the compression. So from the equation P2 is equals to P1 from the equation of number of isentropic RK raised to K. We can get P2. So let's substitute the value. P2 is 7.9 kPa multiplied to the RK 15 and the K 1.33. So our P2 is equals to 3,589.088 kPa. So this is the pressure after the compression. So let's find the mean effective pressure. So for mean effective pressure, we have the equation work net over the volume displaced, or work net is equals to the efficiency multiplied to the QA, or the heat, and the volume displaced V1 over V2. V1 minus V2. So let's find the efficiency. So the efficiency is equals to 1 minus 1 over the RK 15 raised to 1.33 minus 1, and we can get the value, and RC K over 1 K and RC minus 1. So RC is equals to 2.1, K is equals to 1.33, RC is equals to 2.1. So by putting in calculator, we can get the efficiency of 0.5294, or this is 52.94%. So from this equation, our QA, we can derive the equation for QA from this equation. MCP T3 minus T2. So we all know that CP is equals to MCP is equals to K multiplied to R over K minus 1 and our T3 is equals to, from the ideal gas equation, we have P3 V3 over MR and minus P2 V2 over MR. So cancelling, we can get K over, cancelling the value of M, R, K over K minus 1 is equals to P2 V2 and P2 V2 and multiply to RC minus 1. Okay, so this substituting this to the original equation, so we can get the we can have the equation from here. E is equals to K, this one, K over 1, this is the mean effective pressure, minus 1 times P2 V2 times RC minus 1. So this is derived equation. Okay, so over RK, this is from the V2, RK minus 1, cancelling V2, cancelling the volume. So let's substitute the value. We have the efficiency 0.5294 multiply to K 1.33 over 1.33 minus 1 multiply to P2. We have the value of P2 there, 3,589.088 and multiply to RC 2.1 over 1 and RK over RK, we have 15 minus 1. So the mean effective pressure is calculated as 601.687 kilopascal. Okay, so this is the solution. Substituting the value, you can get this one. Okay, so